Hey class, this is me, Mr. Wee. I just want to go through another example with you, or another set of theorems with you for similarity. I apologize. I just spent 20 minutes recording a part and it didn't record, so the mic didn't pick up, so I'm a little frustrated right now. Okay, so last time I believe we left off at an angle-angle similarity, saying that if two triangles have two angles that are congruent to each other, then conclusively you will find out that they are similar. They have sides that are going to be, like, pairs of sides are going to be proportional to each other. Well, we're going to learn two other theorems here, and you can actually copy these down, but that'll take about 5 or 10 minutes to write down. So you can do that while I'm talking, or you can just take a picture of this in your book from page 561. Again, that's page 561 here. You take a picture of this and put it into your your cheat sheet if you want, and print it out to have with you, however you want to take care of this. Okay, but you really need to get these two down, and I don't think we have any proofs or anything, so you don't have to worry about using this in a proof, but just to understand this. So what this is basically saying is that in two triangles, if you can prove that corresponding sides on both the triangles make a ratio, like JL and MQ make a ratio, and if you can compare it to the ratio of other two sides that I think are comparable, so I think JK and MP are corresponding sides in that they make a ratio. If JK and MP make a ratio that is equal to the ratio of LJ to MQ, then so far I have two sides that are similar to each other. And then if those two ratios are equal to the ratio that LK and QP make, again, another pair of corresponding sides, if all three sides make ratios that are equal to each other, that's what we call, not the side SSS congruence theorem, but this is SSS similarity theorem. Again, SSS congruence says that if all three sides are simply equal, like LJ is completely equal to MQ, and then JK is completely equal to MP, then they'd be congruent. But we're not looking at it like that, because we know we can kind of visually see that this triangle is bigger than this triangle, but are they proportional to each other? In order to do that, we have to see if the corresponding sides make a ratio that is equal to the other corresponding sides ratios, and then we can conclude that they are similar triangles, not congruent, but similar. Another way of doing this is the angle side similarity. So let's say that we were only given information for two side lengths of these two triangles, and not the third one. We don't know anything about RT and XZ. We can say that maybe, okay, at least I think SR and YX, or YZ, or YX, I'm sorry, SR and YX, those are corresponding sides. They make a ratio, and that ratio is going to be equal to what ratio that this corresponding side ST and YZ make. ST and YZ make a ratio, and they are equal to each other. And if you can conclude that the angle in between those corresponding sides are congruent, okay, not just equal but congruent, meaning that they're exactly the same in the shape and in the measure, like their angle measure, then if you could say that two ratios of sides, this and this, and a sandwich are proportional to each other, the ratios are proportional to each other with an angle in between them that is completely the same, then by a side angle side similarity theorem can we say that these two triangles are similar. So again, these are just shortcuts to prove that these two, so AA, this is AA, angle, okay, side, and side angle side similarity theorems are all ways to just show you through a shortcut that these two triangles are similar. The long way is to show that all the sides are proportional to each other and all the angles on the inside are completely equal, but you don't need to do that. You just need to prove that all three of the sides are similar, maybe two sides of the similar, or two sides are similar and then with an angle in between that is the same, or you can just prove that two angles are the same in both triangles to prove that both the triangles are proportional and similar to each other. Okay, so let me just show you an example that using SSS right now. So in your notes, you should you should have, this is still in 9-3. So we're going to say, and this is, I'll write this in black, using the SSS and SAS Similarity Theorem. So those are the two theorems we just learned about. So we're going to use them, and here's an example. So here's what you're going to do. You're going to draw two parallel lines. There's one big one, or one small one at the top, and one big one at the bottom. And then we're going to make little corners or vertices, and then we're going to connect the vertices by crisscrossing to each vertex from each vertice. Okay, so these aren't necessarily parallel, but in order to draw them, we're just going to make them look parallel at least. And then we're going to say this is P to Q, and then the middle point is R, and then down here is going to be T and S. Okay, now I'm going to kind of color code these, and I'm going to give you a question. The question is triangle PQR, notice the order in which I'm writing down the letters, is it congruent, or is it similar, not congruent, but is it similar to S to T to R? This tells you, if you are very keen on the order in which I said P to Q to R and S to T to R, it actually inherently tells you which sides are corresponding to the other side. So let me give you some values here. I'm going to intentionally write all these side lengths on PQR in red. So this would be 6, 8, and 5. Or actually, let's see. Let's not do that. Let me get a white out piece right here. So you know what? I'm going to go back. Sorry. I'm going to color code this in a different way, okay? I think that PQ is... So we have two different triangles, ST to R and PQR. I think that PQ and ST are going to be corresponding sides to each other. So I know 6 is going to be comparable to this 15. That's how big they are. Let me give you all the side lengths really quick. PR is, I think, by I is going to be proportional to SR, P to R compared to S to R. Okay, I think, and then I'm going to give you the value which is given to me in the textbook. PR is 8, and then SR is 15. That's both in blue. And then I'm going to say that QR, this is again values that are given to me in the book. Which color do I have right now? I'll say green. QR is going to be 5. And then TR is going to be 12.5. Okay, so again, I think ST, or actually I'm going to, again, I choose, you can do it however you want, but I think I'm a little bit compulsive. I have a little bit of over-compulsive I'm not going to say a disorder. That's a little bit inappropriate to say, but I'm very compulsive about this. So I think I want to go compare from small sides to the bigger sides here, or the small triangle sides to the bigger triangle sides. So I'm going to say that PQ, the ratio that PQ and ST make, I think is going to be comparable or equal to a ratio from PR to SR. Because I think these two sides are corresponding and proportional, and make a ratio with each other. And remember, I'm going from small side over big side, the smaller side corresponding to the bigger side. So smaller triangle corresponding to the bigger triangle. That's the order in which I'm writing the ratios. I can't flip-flop. I can't go from small, so I can't, so let me write this out. So this is going to be PR over ST. So just to forewarn you, if you choose to make a ratio that has a small side to the bigger side, you have to keep that order consistent. So PR and ST, I have to make sure that PR goes on the top as well, because on the numerator of this ratio, just because that's what order I chose to do in the previous ratio that I made. Okay, so in this ratio here, the last ratio is going to be in green. That's QR to TR. Okay, and then let's plug in the values. So PR is going to be 6 over 15. PR, or PQ, is going to be 6. ST is going to be 15. Okay, let's see if that is equal to, is it actually equal to 8 over 15? So PR is 8, and then ST is going to be 15. And is that going to be equal to Q over T, which is going to be 5 over 12.5? Okay, and we have a decimal number, so that might make things a little bit more complicated. So anyways, these don't look equal to each other right now until we simplify them. Oh, and I think I believe I made a mistake. Whoops. I apologize, folks. ST, so let's go back. ST, or SR is going to be 20. Okay. 20. So just going back in here, 8 has to be over 20. Okay, so minor fixed right there. Okay. So let's see. So for anybody picking up on that, nice. That was a good job on you. So I'm going to give you guys some kudos for catching that. But yes, they shouldn't have both been 15. Anyways, let's look at 6 and 15, 6 over 15, and see if we can simplify that. I noticed that the greatest common factor in 6 and 15, a number that can go into both, the biggest number that I could divide into 6 and 15 is 3. So 6 divided by 3 is 2, and then 15 divided by 3 is 5. Okay, so that's the simplest I can go down to. Simplest fraction I can reduce from 615 to. Okay, so let's look at this. 8 divided by 20. I notice that the greatest common factor, the greatest number I can divide into 8 and 20 commonly, is 4. So if I divide 8 divided by 4, that'd be 2, and 20 divided by 5, or 4, I'm sorry, that'd be 5. Sorry about that. So again, both of these numbers can be divided by 4, and I think that's the biggest number you can divide into 8 and 20, and you'd end up with getting 2 over 5. This one's a little bit tougher because we have a fraction on the bottom here. So you have, I see 2 easy options. You can come up with whatever way that makes sense as long as you get the same sort of answer. I know that if I multiply 12.5, because it has a 0.5, if I multiply this by 2, this will automatically get rid of the 0.5 and make this into a nice whole number. I just know that from experience. Now, if you're having any troubles, and let's just say you only have one number after the decimal, I know that if I multiply this by 10, this will move the decimal over to the right once, which basically says that this increased by an order of magnitude of 10. So anyways, to put it shortly, I can multiply both these numbers by 10. And please remember, whatever I multiply on the bottom, I have to multiply on the top, or else it changes the inherent value in this fraction. You don't want to do that. You still want to have the same ratio of numbers. So whatever you multiply on the bottom, you have to do the same thing on the top. So that way the ratio never really changes. Okay, so I'm going to choose to do this. I know that if I multiply the bottom by 2, this will make this into a whole number. But whatever I do on the bottom of this fraction, I have to do the top to make it fair and equal and make this still an equal number. So the bottom divided or times 2 or multiplied to 2 is 25, and then the top number is going to be 5 times 2 would be 10. So there we are. Now, these still don't look very similar. These two look similar. This one is the last one, but we haven't reduced it yet. So now that we have a form that we can reduce into, let's ask the question, what is the greatest common factor in 10 and 25? What number can divide into both of them? And what's the biggest number that can divide into both of them? Well, I see that they're both divisible by 5, and that's probably the biggest number that I can divide into both of them. So 10 divided by 5 is 2, and 25 divided by 5 is 5. There you have it. 2 over 5 is equal to 2 over 5 and 2 over 5. So I've concluded that the 3 pairs of sides that I find are corresponding to each other make a ratio that is 2 over 5, 2 over 5, and 2 over 5 that are all proportional to each other. So what that means is I just exercised. So this is you don't have to write this statement, okay? But you can say that this is a therefore statement. You can write this down if this makes sense to you. Therefore, by the Sss Similarity Theorem, THM for short, for theorem for short, triangle PQR, remember that was the whole point of this problem, was to see, well, this was a question, are these triangles similar to each other? And then we can appropriately answer by the Sss Similarity Theorem, PQR is similar to triangle STR. You don't have to write this down in the test, but that would be really nice if you did. Or in the future, this is just a very formal statement, because here I could see in the math, this concludes, yeah, you can just do this. This concludes that, yes, these two triangles are similar to each other. But if you're have a nice little statement, it's like a bow on your gift that you're giving to your teacher or whoever you're working for. When you're creating shapes and you're trying to prove shapes are similar to each other, you can say by the side-side-side similarity theorem that these two triangles are going to be similar. Okay, so that's going to be an example I give to you, but I'm going to give you your own problem that you can work on at home, or you can work on in class with a partner. So you can pause this part after I write it down, this next example I'm going to write down, and then you can work on it. Or if you feel like you just want to move on to the next part, go ahead and stop this video at this point and move on to the next part. But again, I'm going to go through one more problem, okay? And remember, we've only went through the SSS similarity theorem. Let's go through a scenario where you might need to use the SAS similarity theorem. Just a little hint there, okay? So I'm going to draw a giant triangle here. It looks like a right triangle, but I'm not going to say it is, because we don't know if it is or it isn't. And then I'm going to run a line that is parallel to the bottom baseline there. I'm going to say that this is A. This is definitely not to scale very well. A, C to B. And then to here, it's going to be E to F. Okay? And then I'm going to ask you if there are two triangles that are similar to each other, but I'm going to tell you which ones I want. Is A, E to F, I'm going to color code that in green, is that similar to A to C to B? Okay, so if you want to work on this, go ahead. You can pause this now and then unpause it after a few seconds and see what happens, or you can move on. Okay, so go ahead and pause it if you want to work on this one. Okay, so hopefully you've unpaused it by now. Oh, whoops. Oh, actually, I'm super sorry, guys. I didn't even give you any values, so that wouldn't really make any sense. Oh dear. Hopefully you did not pause this, so I totally apologize. Let me give you the values. Doesn't make any sense I didn't give you any values. So this should have been 8, 10, and this is 4 and 5. Okay. Oh dear. Mr. Wade made a huge boo-boo. So if you haven't paused it and you kind of had an intuition that I did something wrong, now you can pause it. That's the only information that should be given to you. I did not give you anything about EF and CB. That was deliberate, okay? So now, if you're still with me, go ahead and pause it and then unpause and work on this one, okay? All right, and hopefully you're unpausing me now if you're still with me, and then you can work on this problem. The first thing to notice, or maybe, let's see, is that, or if you're having problems visualizing the triangle, first, why don't we spread apart these two triangles? So that's why I color coded this in green. A to E to F, I'm going to say, is in green. It's slightly smaller. So if I separate it out into a separate triangle, this is what I got. A to E to F, and then this is 8 and 10. Again, we don't know this side, EF. And I'm going to do the bigger triangle in red, which is A to C to B. A to C to B is quite a bit bigger. Sorry, I just don't have enough room here, but let's see. A to C to B. And then, truthfully though, what is the measure of A to C? Well, it has AE 8, and it has this little segment 4. What I'm going to do is I'm going to say that this whole segment A to C is a combination of this side AE that's 8 units long, and E to C, which is 4 units long. So in total, this is going to be 12 units long. A to B is simply a combination of this side that's 10 units long, which is AF, and FB, which is 5 units long. So in total, 10 plus 5, that's going to be 15. Now, I think some of you guys are wondering, oh, why don't I just do the Pythagorean Theorem, Mr. Wade, and find out these two sides down here? Just to let you know, I did not say that this was a right triangle. I just say draw it as if it's a right triangle, but they are not right triangles. So don't do that. The Pythagorean Theorem only works if this is confirmed this is a right triangle. I did not confirm that these are indeed right triangles. So you're only left with this about information. But there's one huge vital piece of information, is that they both share angle A. So if you can see, that means that angle A on both of these guys separated are going to be congruent to each other. That's a gimme right there. Because they're drawn and overlapped perfectly on top of each other, angles A on this triangle and is the same thing as the angle A on this triangle. Again, that's not the reflexive property, by the way. Oh, actually, I believe it is. No, I'm super wrong. Yeah, because they share that. That is by the reflexive property. Ah, Mr. Wade, you made so many mistakes in your videos. What's wrong with you? So the first statement I'm going to make is that angle A and I'm going to color code it so you understand that they belong to different triangles. Angle A on the green triangle is going to be not just similar, but completely congruent to the shape and the measure of angle A on the other red triangle, on the ACB triangle. Okay, that's the first statement I can make. The second statement I'm going to start making is saying I think that the ratio of A to E and AC are going to be, they make a ratio A to E over, I just chose to do small side over the big side, corresponding big side to A to C. I think that that ratio between these two sides is going to be equal to the ratio of these two sides over here. But let's see if it is. So I'm going to say this is A to F over A to B. Okay, so I think the ratio of these two sides is going to be equal to the ratio of these two sides, or proportional. Okay, so I'm going to put in some values. So I'm going to rewrite this whole kind of statement here. I'm going to rewrite it off to the right here because I'm running out of space on my paper. So AE is going to be 8 divided by, and then AC is going to be 12. Okay, so I'm substituting in values for AE and AC. And let's see if that is going to be equal to the ratio from AF over AB, which is 10 divided by 15. A lot of color coding here. Okay. Well, they don't look similar yet, but let's reduce these into its simplest forms. So this ratio here, I notice 8 divided by 12. 8 divided by 12, I know that both these numbers are divisible by 4, so the greatest common factor I think is 4. So I think 8 can be divided by 4 twice, and then 12 can be divided by 4 3 times. There we go. So my total ratio is going to be 2 over 3. Okay, I'm going to write this in black as a final ratio of this guy. And then over here, 10 over 15, I know that they're both divisible by 5, and it looks like the greatest common factor, the greatest number that can divide into both of them equally, or not equally, but they can just divide into it cleanly, is going to be 5. So 10 divided by 5 is 2, and then 5 divided by 5 is 3. So guess what? I have two pairs of sides, A and AC, and AF and A to F and A to B are proportional to each other, and in between those proportional sides is an angle that is congruent. I have that in my first statement here. Congruent angle sandwiched between two sides that are proportional to each other. So what that says is in conclusion, by the SAS, that is by definition a side angle side similarity, by this SAS similarity, side angle side similarity theorem, triangles AEF, like my original question was asking, it was asking in this, is triangle AEF similar to ACB? Well, yes, by the SAS similarity theorem, triangle AEF is indeed similar to ACB. Okay, guys, you guys can go ahead and stop and move on to the next part. All right, thanks for joining me, guys. I'm going to go ahead and stop this right now.